Hello, I'm Nick Turner.
And I'm Matt Sorokin.
Today we'll be discussing the production of single-walled carbon nanotubes using the HiPco process. You will learn about the exciting potential of carbon nanotubes, the HiPco process, and why it is a promising method for industrial-scale nanotube production. To begin, carbon nanotubes are composed of chains of carbon atoms which form a tube-like structure. This animation demonstrates the structure of the nanotube at the atomic scale. Carbon nanotubes, or CNT for short, are at the cutting edge for material science research. This is due to their attractive physical properties such as their extremely high strength, conductivity, and aspect ratio. Some current applications involving CNTs include computer chips, bone healing, body armor, solar cells, capacitors, and cancer treatments. Note that this list is not comprehensive.
In this video, a researcher demonstrates a nanotube-based artificial muscle.
Another area where nanotubes have potential is cancer treatment. This is done using specially functionalized nanotubes. These nanotubes are injected into the tumor site and enter the cancer cells. When these nanotubes are accepted into the cancer cell, the cell is exposed to infrared radiation. This radiation excites the tubes and results in explosive destruction of the tubes. This explosion also causes the death of the cancer cell. There are several methods used to produce carbon nanotubes. The first is known as laser ablation. This method uses a high-power laser to vaporize a graphite source loaded with a metal catalyst. The carbon in the graphite reforms single-walled nanotubes on the metal catalyst particles. The second is arc discharge, which involves an electrical discharge from the carbon-based electrode in a suitable atmosphere to produce both single and multi-wall tubes of high quality but low quantities. The last and most important is known as chemical vapor deposition, or CVD. This is a process where hydrocarbon feedstock is reacted with a suitable metal-based catalyst in a hot furnace to grow nanotubes, which are subsequently removed from the substrate and catalyst by a simple acid wash. The HiPco process is a form of CVD and is one of the strongest candidates for large-scale industrial production of single-walled nanotubes. This is due to the high production yield and purity of the resulting product.
So what is the HiPco process? HiPco stands for high-pressure carbon monoxide, which serves as the carbon source for nanotube growth. Iron in the form of iron pentacarbonyl is used as the metal catalyst. Carbon atoms dissociate from carbon monoxide to form nanotubes through the boudoir reaction. The second law of thermodynamics states that a reaction will go spontaneously if the overall entropy of the universe increases ideally. Whether or not this occurs depends on the thermodynamic conditions within the reactor. Maximum production efficiency can be achieved by optimizing several of these parameters. We'll take a look at several plots used to determine the ideal conditions. Since CO2 yield is proportional to CNT yield, it is used as a marker of CNT production. This chart shows the dependence of yield on reactor temperature. We can see that maximum production is achieved at around 1050 degrees C. Here, the effect of iron pentacarbonyl concentration is examined. Production peaks at a 1-to-1 ratio of iron pentacarbonyl to carbon monoxide. Production rises again at higher concentrations, but this effect is accompanied by higher amounts of impurities, so the initial peak is ideal. This plot shows that CNT yield increases linearly with respect to CO pressure. As a result, this pressure is constrained only by the durability of the reactor. This is a diagram depicting the HiPco reactor. The showerhead simultaneously delivers heated carbon monoxide and a mixture of room temperature carbon monoxide and iron pentacarbonyl into a long quartz tube heated with resistance coils, whose power is adjusted by feedback from thermocouples embedded near the showerhead. The output from the reactor then passes through a series of filters and fluid surfaces to collect the product. Next, we're going to show an animation portraying the nanoscale behavior that occurs throughout the HiPco process. First, the iron pentacarbonyl molecules undergo thermal decomposition, releasing iron atoms. The iron atoms nucleate and then undergo surface growth through free energy gradient diffusion, forming nanoscopic clusters. The iron clusters act as catalytic nucleation sites for carbon that is dissociated from carbon monoxide through the boudoir reaction. Carbon atoms are added at the carbon-iron interface, resulting in growth of the nanotube. The diameter of the resulting nanotubes is typically around 1 nanometer. It is determined by the size of the catalyzing iron cluster during carbon nucleation. The final product is a loose black felt consisting of single-walled carbon nanotube ropes interspersed with carbon-coated metal particles. These are images of the nanotubes obtained using transmission electron microscopy. The dark spots in the image are the ion clusters. These products can now be purified and sent out to customers. So that concludes our summary of the HiPco process. We hope you learned something about how carbon nanotubes are made and why they're important.